Hi everybody, my name's Kat. I'm your lab TA for MCG2360B. This is the first video of what will be four. Each video is associated with a specific lab, so you can either attend the lab and see the experiment done in person, or you can watch the video through Brightspace and you should get the same information. You'll have to bear with me because we haven't done things this way before, so it's a bit of a learning experience for me and for all of us. So if you notice anything, or if there are any problems, if you're having trouble understanding anything, please do not hesitate to email me or call my extension. Come to my office hours. I want to get this right, so yeah, please don't hesitate to contact me. So I'll dive right into what we're doing today. Lab 1 is called tensile test. So this experiment is going to be your introduction to tensile testing in material science. So this is the Instron 4482. It is the materials testing machine that you will use most often during your undergraduate degree. You can see it's quite large, over 6 feet tall, and I've lit up the testing area with a lamp in front of it. So if we come in close to the testing area, you can see that there is a top piece and a base. The base is fixed while the top can extend or it can be lowered. So if you look on the right hand side where my hand is, you'll see there's a little toggle button, and this is what we use to control the top piece of the Instron. And here you see it's extending, fracture, and then I'm bringing it back down. If we zoom in here and look on the sides of the machine, you can see the screw that allows the top component to raise and lower from our controls. If we look on top of the machine, there's something called a load cell. So this is what measures the force being applied to our sample. You can see that this one is a static load cell with a 100 kilonewton limit. If you look over on the right hand side of the machine, you see this red button. This is our emergency stop. It will stop all testing if something happens, something gets caught in the machine. So just be aware that we usually have these buttons. Earlier, I mentioned that we have the load cell on the top piece of the Instron, the part that raises up and down. So this is recording our force data, and then the Instron is also recording information on the position of that top piece. So this becomes our extension or our displacement information. And these two streams of data are sent into the computer that is sitting beside the machine waiting to start up some testing. So you can see I've got a little graph here, and it says load on the y-axis and extension on the x-axis, and this is where our data is going to pop up once we start running our test. So more generally, what I'm doing is I'm introducing you guys to the tensile test. It is a very important test in mechanical engineering, and you can see it over and over and over again. I'm working with it right now in human tissues as a part of my PhD, so it's not going away. So this is your first chance to see it and familiarize yourself with it. And then more specifically, we want to study the relationship between stress and strain in ductile and brittle material specimens of cylindrical geometry. So if I were to write my purpose down in my lab report, I would say something like that. So we have these two samples that I showed you guys already. We have our, I'll flip them back. We have our steel and our aluminum. So we are going to use a quasi-static uniaxial tensile test to try to understand what's going on with these two materials. How are they similar? How are they different? And how does this manifest in their stress-strain curves? We're also going to take observations of elastic behavior, yield, necking, and fracture or failure behavior. So we're going to observe all of this in comparison between a more ductile material and a more brittle material. So we have two samples that we're going to be working with today. We have a lighter colored, lighter in weight aluminum, so it's an annealed aluminum, 6061-0, and then we have a steel sample. So this is a low carbon 1018 steel, also annealed, which is darker in color. It weighs more, so I can feel when I hold the samples that this guy weighs a lot more. And you can see, looking at the samples, they are the same size. They've been machined exactly the same way. So they have threaded attachments at the top and the base, and they are cylindrical in shape. Before we can start our testing, we need to take measurements on the dimensions of our samples. Like I said, the Instron machine records force and position of our top piece in our apparatus here, but what we need for our understanding of the material is stress versus strain. So we've seen in class that force divided by the cross-sectional area of our sample gives us the stress, and the change in length over the initial length of our sample gives us the strain. So in order to calculate stress and strain, we're going to have to measure these initial dimensions on our samples. So I'm going to take my calipers and my steel sample that I have right here, and I will measure the diameter of the sample to be 12.75 millimeters. And then if you look closely, you can see we have a couple lines here on the sample, over here and on the other side over here. So I'm going to measure those distance between the lines to get the initial gauge length of the sample. So I'm going to measure that, and it will be 50.85 millimeters. And then I'm going to do the same thing for my aluminum sample. I'm going to grab that and measure this as well. So again, diameter 12.65 millimeters. And the length is, same thing again, I'm going to measure from those two lines. 50.75 millimeters. Now that we've got that information written down, we can test our samples. So I'm going to start with the aluminum. I'm going to install it in the machine. So these are threaded attachments right here. You can kind of see that. So this guy with its threaded ends is going to get just screwed right in. As well, I'll do the same thing for the top piece. And then I'm gonna place these back in the machine, and then I'm gonna start the testing. So now the machine, the top piece is moving upwards at a rate of 10 millimeters per minute. And we're collecting the force and position data on the computer. You can see that the sample is starting to neck. I'm going to zoom in here. There we go. So the sample is starting to neck, which is characteristic of more ductile materials. And that's fracture right there. So on one side, we can see that there are these little lines almost on the surface in comparison to over here, which was fixed in the machine. We have a change in texture. We have a change in color. I'm not sure if we're going to be able to get this. Yeah, there we are. The actual fracture surface is a little rough. And it's like that on both sides. So if I bring the other side, this is the second half of the same sample. We see those little lines again. We see the rough little cup kind of shape. Those rough edges. And then again, compared to what was a smooth and uniform surface before we strained it. So we can see that there's a big change here due to the tensile stress on our specimen. Now we can do this all again for our steel sample. So I'll do the same thing over. I'm gonna place the sample in the machine. Okay, so we've got our steel sample in the machine, and we're gonna start our test with the same parameters. So we're gonna extend at 10 millimeters per minute, and we'll see what happens with our steel. So the test is running. I'm gonna zoom in here a little bit so we can watch what happens. So we're starting to see a slight necking with our steel as well. Maybe not as prominent as with the aluminum, but maybe pretty similar. Holy shit. And that much louder noise was the fracture of our steel sample. Here we go. Okay, so we've got our steel. You can see that there's still a change in the texture of the surface. It's a little bit different than before. We still have a change in the color of the fracture surface compared to the original sample. We'll look at the other end as well. There we go. So this is our other half. We can see, and I'll hold those up beside each other. So there we go, aluminum. So we've got aluminum on top and steel on the bottom. So you can see that although we had a change in the material near the fracture surface for the steel, it's not nearly as pronounced as with the aluminum sample. As well, let's look at our fracture surfaces.